All right, hello all. I wanted to make a quick video to help with transformations. So we did an activity in class today to help kind of figure out how these transformations work. We've seen these before, so hopefully this is just kind of refreshing your memory and knocking the rust off. So this table is a great summary of all of the transformations. Um, Basically, if you what changes you make to the equation is over here, and the effect on the graph is over here. We ran through a lot of these. I don't want to go kind of line by line here, um, but I do kind of want to point out sometimes this notation is confusing. I want to give you an equation to show you what this would look like in practice. So let's say we had the equation y equals x squared. So if I do a vertical shift, that happens when you add a constant, a number, to the outside of the function. So what that would look like is if we had x squared plus 3. This would be a vertical shift of the function x squared. Similarly, if you subtracted a number like -3, that would shift us down 3. Again, these happen outside of the structure of the function. Since we have a squared here, that's what provides the structure. Now, a horizontal shift, this happens inside the function with x. So what does that look like in practice? So if we have the equation x squared, the function itself is this exponent of 2, and I would want to subtract a number inside the exponent with x. So basically, I would introduce parentheses here, and I would do x minus 3, say, to the second power. This minus 3 would shift us to the right by 3 units. Similarly, if I was inside and I had x plus 3 squared, that would shift us to the left. Multiplying by a number outside the function gives us vertical stretching and shrinking, so y would equal 3 times x squared. This is a multiplying on the outside of a function. Because this number is bigger than 1, it would vertically stretch us. It would multiply the distance from the x-axis by 3. Um, this guy, a horizontal stretch or shrink, that would look like multiplying inside with x. Again, because my structure here is a second power, it would be multiplying underneath that exponent with x. So both the 3 and the x would be squared here. So this would give us horizontal stretching or shrinking. Since this number being multiplied is bigger than 1, this would actually give us a horizontal shrink. And this would divide your distance from the y-axis by 3. It pushes you closer to the y-axis, and you divide by whatever that number is. You would basically divide your x-coordinate by that number to figure out where it goes. And then the reflections are negatives. If you have a negative on the outside, that looks like this for the function x squared. That's the negative on the outside. That reflects you across the x-axis. And having a negative on the inside would look like this, and that would reflect you across the y-axis. Again, anything where the constant c or the negative is happening on the outside of a function, like these guys, or here, or here, these are all going to be vertical changes. So you either shift up and down vertically, you stretch or shrink vertically, or you reflect up and down over the x-axis. Anything where you have the constant happening on the inside with x, like this one, or here the negative is on the inside, these are going to be horizontal changes. So if you add or subtract, that shifts you horizontally. If you multiply inside, that's going to horizontally stretch or shrink you. And if you have a negative inside, that is going to reflect you horizontally across the y-axis. Okay, so that's what all of that stuff means. If we have multiple transformations happening, you have to do them in the correct order to make sure that you have the right answer in the end. So the first thing that you want to do is graph your base back pocket function. To find your base back pocket function, you would basically cover up or remove everything in the equation that's not a transformation, and what you're left with is your base back pocket function. And it's going to be one of our back pocket functions. It would be y equals x squared, y equals the square root of x, y equals the absolute value of x, y equals x cubed. It's going to be one of those guys. Once you have your base back pocket function graphed, the first thing that you want to do is you want to perform any horizontal shifting. So if you slide your whole function, I can spell shifting, if there's any sliding to the left and right that needs to be performed, you do that first. And then after you slide to the left and the right, the next thing that you want to do is perform all the stretching and shrinking. So you'll want to do both vertical and horizontal stretching or shrinking, whatever you have. Do them both during this stage. Doesn't matter which order you do them in, but your stretching and your shrinking will happen after you do that horizontal shifting. After you do your horizontal shifting and any stretching or shrinking, the next item that you're going to do is going to do all reflections. That's what you want to do next. Again, any reflections across X or across Y. If you have both, you can do them in any order, but you'll do them after any stretching or shrinking. And the very last thing that you're going to do is any vertical shifting. This is the one that you want to save for last. Sliding your graph up and down is the very last thing that you want to do. Big thing is that you do the horizontal shifting first and the vertical shifting last. If you do 3 and 4 in the wrong order, it actually won't change your graph at all. You're going to get the right answer. But if you don't do the horizontal shifting first and the vertical shifting last, it will make a difference in your graph. So that's the order that you want to do these transformations in. And let's try an example so that we can see this. So we'll do number 1 here. Graph each transformed graph. Okay, so n of x equals -1/2 times x minus 2 squared plus 3. All right, I'm going to start out and just try to identify what some of these transformations are. I have a negative out front. That means we are going to reflect. It's on the outside, which means it's going to be a vertical reflection. So we're going to reflect up and down over the x-axis. I have a 1/2 out here. That's multiplying by a number on the outside of my function. That's going to be a stretch or shrink, and it's going to be vertical because it's on the outside. So a vertical stretch or shrink, is it going to be a stretch or a shrink? Well, because this is a fraction, it's going to be a vertical shrink. It's going to basically squish everything closer to the x-axis. It's going to take however far away from the x-axis we are and cut it in half. All right, I have a -2 in here with x because I'm subtracting inside with x. That's going to be a horizontal shift, and it's going to go the opposite way you think it will. So a -2 is going to move us to the right by 2 units. And this +3 out here, because I'm adding a number on the outside, that's going to shift us up and down. And this is going to go the way you think it will. So that is going to shift us up by 3 units. Okay, so now what's my base function? The very first thing that I need to do here is graph my base function. What is my base? Okay, so to figure out what that is, we are basically going to take anything. Let's pick a different color here. I'm going to try to erase. And so anything that creates a transformation I'm going to cover up. So this negative creates a transformation. This 1/2 creates a transformation. This -2 creates a transformation. And this +3 creates a transformation. What am I left with when I remove all the stuff that makes a transformation? What I'm left with is y equals x squared. Do you see that? That is the only things that I'm left with. The x and the exponent of 2, x squared. That's my base function. That's a back pocket function. That's my base. Okay, so that's how you find your base function. Cover up anything that is a transformation, and it'll show you what structure is left, and that's your base. Okay, so now I'm going to graph my base function, y equals x squared. Just going to kind of set up my axes here. Okay, y equals x squared. This is a back pocket function. I know I'm going to go through these points. Again, if you're not sure which points are which, pick some x values, plug them in and see what you get, and then plot those points. Here's y equals x squared. Okay, so now that we have y equals x squared, what do we do next? Well, we're going to do any horizontal shifting first. We do have some horizontal shifting, so I'm going to shift this thing to the right by 2 units. That's the next thing I'm going to do. I'm going to take each of my points here, and I'm going to slide it over 2. 1, 2, 1, 2, 1, 2, and 1, 2. Now I will draw my graph, and I shifted this whole thing to the right by 2 units. Okay, after I do horizontal shifting, the next thing that I'm going to do is any stretching or shrinking. I do have a vertical shrink happening, so I am going to vertically shrink this. I'm going to cut every point. I'm going to squish everything half the distance from the x-axis. So I'll start here with this point. Right now, this is 4 units away from the x-axis. So I'm going to cut that in half, and I'm going to bring that down to 2 units from the x-axis. I'll come here to 1, 1. If I cut that in half, I'm going to go to 1, 1/2. Here on the x-axis, this is 0 units from the x-axis. If I cut that in half, I am still at 0. Here, this is a distance of 1 unit from the x-axis. I'm going to cut that in half and bring it halfway down. And on this point, I'm going to take this one. It's 4 units from the x-axis, and I'm going to cut that in half and bring it down to 2 units from the x-axis. Now I can connect these. And basically what this does is it makes my parabola open wider. That's what a vertical shrink does for a parabola. Okay, so I've done my vertical shrinking. I don't have any horizontal stretching or shrinking, so I don't have to worry about that. The next thing I need to do is any reflections. I do have a reflection over the x-axis, so I'm going to take each of these points and I'm going to flip them vertically across the x-axis. So this point is 2 units above, so I'm going to move that to 2 units below. This is half a unit above, so I'm going to move it to half a unit below. If I flip this over, it still stays where it is. This one flips to halfway below, and this switches to 2 units below. Basically, the distance stays the same. You're just going to put it on the other side of the x-axis. Okay, so now I'm going to connect these guys. We are almost there. And now that I've done the reflections, the very last thing that I need to do is any vertical shifting. So the last thing I'm going to do is push this up 3 units. So I'm going to take each point and I'm going to go up 1, 2, 3. This point goes up 1, 2, 3. This goes up 1, 2, 3. 1, 2, 3, and 1, 2, 3. And then connect these. All right. I have now done all of my transformations. This black one is the correct one. And because there's so many kind of different parabolas on here, I'm going to make a clean version of this. And I'm going to just redraw my final answer so that it's clear. And let's see, I've got the 0.01 here. I've got the 0.1, 2.5. I've got the 0.2, 3. I have 3, 2.5. And I have 4, 1. All right, and that is my final parabola. This is what my transformed graph looks like. All right, so that's kind of the process that you want to use. There's a few different ways that Alex is going to test you on this. One of those ways is that it might not give you a function algebraically. It might give you a graph of a strange function and then just ask you to make the transformations. So you won't have to do that first part of graphing the base. You'll just have to make the transformations with what you're given, but you're still going to have to do them in the right order. All right, I hope this is helpful for transformations of graphs, and happy studying, and I'll see you next week.